Hi everybody, this lesson here we're going to talk about working with definite integrals, so that's the area underneath the curve, and specifically we're going to talk about two things, mainly the properties of definite integrals and then another theorem called the mean value theorem, but this is the mean value theorem for integrals. So first thing we'll talk about here are some of the basic properties. These are for even and odd functions, and these are pretty quick because you can verify them with a nice diagram. So two of the common properties that you'll find in a lot of calculus books is if the function is even and then also if the function is odd, then if you integrate over an interval that is symmetric about the origin, then they have certain properties. So this first one here says that if f is an even function, then if you integrate from negative a to positive a, it's the same thing as integrating from 0 to a, but you can double the answer. So a quick diagram here confirms this. So you might remember from algebra, even functions are functions that are symmetric with respect to the y-axis. So whatever you see on one side of the y-axis, you're going to see the same thing on the other side. So if you think about integrating from something like negative 3 to positive 3, then whatever area you get here, symmetrically you're going to get the same area here. So this is just a nice computational shortcut where you can integrate from 0 to wherever on the right-hand side, and you can take this area here and you can simply double it. So that's just a property of the shape of the function. And then the second property, if f is an odd function, so you can think about things like y equals x or y equals x cubed, then when you integrate from negative a to positive a, you get nothing at all. So the integral evaluates to 0. So a quick look at that diagram, and this should be confirmed. So remember that odd functions are symmetric with respect to the origin. So you can see this diagram here is the graph of y equals x cubed. So in this picture we're integrating from about negative 1.75 to positive 1.75. And so you might remember some of the other things that we've talked about. This area, right, is going to contribute in a positive way, and then this area that lives underneath the x-axis contributes in a negative way. But you can tell that these two areas are the same. So whatever value you get here and here, you get different signs, right? So these two will cancel out as quantities, and the result of the integral, it'll evaluate to 0. So the only thing you have to watch out for with these properties, right, for even functions and for odd functions, these shortcuts are great, but you do have to make sure that you realize that they're only valid on the symmetric window. So things like negative 5 to 5 or negative 7 to 7. So if you have an integration window that might be, say, negative 3 to positive 4, you can still use these properties, but you have to use them with care. So you can actually only use the property when the window there is symmetric. Alright, so the other part of this lesson here is the statement of the mean value theorem. So I'm going to put the old one up, and this here is from the derivative lesson, right? So when we were talking about differentiation, we had this very important theorem that was important both with respect to theory and application. So this thing here is called the mean value theorem. We had a continuous function on an interval, and this existence theorem told us there's a number c, right, somewhere in the interval ab where f prime of c is equal to this quantity here. And you might remember some of the old discussion. This here gives us the slope of the secant line through the endpoints that go through a and b. And this is the slope of the tangent line. And the theorem geometrically tells us that there exists some location where the steepness of the tangent line is going to match perfectly the steepness of the secant line. So these two lines here are going to be parallel lines. And so with respect to application, this is telling us instantaneous rate of change is going to match the average rate of change. So what I'm going to do with this theorem is we're going to take a minute here and just apply it to capital F, because we've been talking about antiderivatives. So I'm going to rewrite this statement here. Instead of the little f, I'm going to write down capital F. So it's going to take on this look here. Right? So this theorem here will apply to any function that is continuous. So all I'm doing here is just applying this theorem to a new kind of function, what we call the antiderivative of the little f function. So this has the same look as this here. The only difference is we have capital F in place of little f. And then there might be a couple of things that you recognize right away. I'll get rid of this. So one thing here is this evokes the fundamental theorem of calculus, right? The f of b minus the f of a. So this makes you think of the area underneath the curve. So we think of area there. And then some of the older things that we've talked about, f prime, if capital F is an antiderivative for little f, then the statement that we know from a while ago, capital F prime is the same as little f. So if we wanted to rewrite the mean value theorem in a different way, we could replace capital F prime with little f, and then in place of this, we could use the integral notation, right, the area underneath the curve. So if we rewrite it that way, it's going to have a different look to it. So it'll look like f of c, and then here I'm going to use the integral notation, integrate from a to b, f of x dx, right, because that'll be f of b minus f of a, and then divide by b minus a. And then what we could do here is just multiply both sides by b minus a, and this is the way you'll usually find this written in books. Right? So multiply by b minus a, and then you're left just with the integral here. So integrate from a to b of f of x dx. So this statement here, remember here that this is the same as the old mean value theorem. All we did was replace little f with capital F, right? Just letting it play that role, and then we have this statement. So it should make sense here that this has a slightly different interpretation. This we know is the area underneath the curve. So we could go from a to b, for example, and you could have some function that might look like this. We'll call this f. Right, so this thing on the right hand side just represents the area underneath it. So we can interpret it this way here. And then on the left hand side, b minus a, this is simply the length of the interval, right, from a to b. It represents that width. And then we always interpret things like f of c as a y value. So this here represents a height. So if you think about a width and a height, this reminds us of rectangles. And it's really telling us that there is a specific rectangle where if you take this height and you multiply by the entire width, b minus a, then it's exactly equal to the area underneath the curve. So just in a diagram, this is sometimes tough to detect. I'm guessing in this picture would be right around here. So if you go up here and you locate this position here, the height of this would be f of c. So we can draw a rectangle, just like this. And the argument here is if you take the area underneath the rectangle, that's going to be the same as the area underneath the curve. So just thinking about this part here. So this area here of the rectangle is equal to the area underneath the curve. And you can tell that there's a little balancing act here where this area that's outside of the rectangle is compensated by this area here that is not under the curve. So it's this thing here that we call f of c. Right? That is that little height. And so this has a very common and appropriate name in mathematics. So this f of c here we call the average value of the function. Because notice that it's trying to capture the fact that the function is growing, and it seems to capture that, that location, that y value that is right in the middle. So this f of c here, this is the average value. And what we usually say, it's the average value of the function f on the interval, right, from a to b. So we should take a look at an example of this with an actual f and some interval a to b, so that way we can make some sense of it. So here's the example I'd like to do. This one here is saying straight ahead, just find the average value, right? So find that special value for this function, not a terribly difficult one, but the function is 3 minus the sine of x. And we're going to find the average value of the function on this window from 0 to 4, and then try to give an interpretation as well. Alright, so if we just look back at the, what we just talked about, the average value, the way we can calculate this. So the average value here is going to equal this integral, right? We have to integrate this function over this window. So it's going to integrate from 0 to 4, 3 minus the sine of x dx. And then we have to divide by b minus a. So in this case it would be 4 minus 0. So this here is what we called f of c when we talked about the mean value theorem. So we have the area underneath the curve divided by the size of the interval. And you might notice if you think about the meaning of this term, right, average value, then what we usually do when we average things is we add everything up. We add up our data, and then we divide by the number of data points that we have. And so if you look at this setup, what we're doing here is we're really adding up the areas of all of these rectangles and then dividing by the size of the interval. So all we have to do here is to calculate this on the right-hand side, and that's going to give us the average value of this function on this window. So I'm just going to focus on this. We're integrating and we're dividing by 4. So I would write it this way. So it's 1/4, and then we're going to integrate. So this one doesn't look too difficult, right? The antiderivatives here are pretty basic. So the 1/4 is going to carry down into the problem. Antiderivative here, this would be 3x, and the opposite sign would come from positive cosine. So we always think of this, the derivative of cosine would be opposite sign, and then we are using the fundamental theorem of calculus, right? So you can put in 4 and 0 and then just calculate this. So we'll put in a 4, and this will give us 12 plus the cosine of 4, and then we'll have to subtract off what we get when we plug in 0. So when you plug in 0 here, we get 0 and then plus the cosine of 0. So we have to watch that. So 0 plus cosine of 0 will be 1. So you have to be careful there. So it looks like we get 12 minus 1, which is 11. So what we're getting here would be 11 plus the cosine of 4. And then we have to cut that answer by 4. So at this point you can go on a calculator just to determine what this value is. It's around 2.6. So 2.59 here. So that is the average value, right, of this function, 3 minus the sine of x, if you stay on this window from 0 to 4. So what we should do is just to take a look at, in a diagram, right, how we would interpret this number, this 2.59. So what I've done here in this diagram, a couple of things. So this little function here that oscillates just a little bit, right, from 0 to 4, that is the graph of this function here, the little f, so 3 minus the sine of x. Notice it starts at 3 and it dips a little bit and then it climbs almost to 4. So that's the graph of this function. And then what I did on the same set of axes is to graph this straight line, y equals 2.59. So you can see this perfectly horizontal line that shows up right here. So what we're saying is that this horizontal line is meant to capture the essence of what this function is doing. So this function dips below the line and it has values above it, but this here is what we would call the average value of the function. So if you think about this in terms of area, we would say that the area underneath this function from 0 to 4 is exactly equal to the area of this rectangle if we were to construct a rectangle, and that's why this number, 2.59, is a special value. So if you think about this graphic here, I'm trying to illustrate this in color, right? So this is the exact same graph as the previous one, except with some color. So what I did is the area underneath 3 minus the sine of x, this little portion here, I shaded in yellow, and that's going to be equal to some value. And then the area of just the rectangular portion, right, so just under y equals 2.6, that I shaded in red. And then you can see anything that shows up in orange is a combination of both the yellow and the red. So this orange portion is common to both, and because this is the average value, what it's really telling us is if you calculate the area of what we see in yellow here, that's going to be equal to the area in red, because the area of the rectangle is exactly equal to the area underneath the curve.